Last time we solved the one-dimensional harmonic oscillator in the Schrodinger equation using the raising and lowering operators, the sort of elegant algebraic method. Today we're going to do the brute force differential equation method in part 2 of the harmonic oscillator. So we'll start again with Schrodinger equation. Our potential again, 1/2 mx m omega squared x squared. I'm going to put in I'll do a change of variable. I'm going to put in a dimensionless variable c, and I'm going to write that as m omega over h bar times x. Don't worry, we'll be making about 12 variable substitutions before we're done here. I can rewrite the Schrodinger equation then as d squared psi dc squared is equal to c squared minus k times psi, where I'm going to define k as 2e over h bar omega. So it makes it look a little bit easier. It's not really any easier, but it makes it look a little cleaner. And what I need to do then, the bottom line is, since you see that k is some function of e, if I can find k, then I'll be able to determine the eigenvalues of the harmonic oscillator. Now, we know what they are. We did that last time, but for sure we want to make sure that we get the same answers. Okay, so let's look at this differential. It's not so simple to solve this right off, but we can do an approximation, and it will make life at least a little bit easier. Let's suppose, as a first approximation, suppose that c is very large, so that the first term more than dominates the second term. If that's the case, I can rewrite my differential equation as second derivative of psi with respect to c gives me c squared. I can solve this using my differential operator, so I can write this as d squared psi, second derivative of psi is equal to c squared psi. Factor it, we'll get d squared minus c squared psi is equal to 0. And of course I can factor that, d plus c, d minus c is equal to 0, which gives me two differential equations. So I have d psi dc is equal to minus c times psi, and d psi dc is equal to plus c times psi. That tells me that I can write psi as e to the minus c squared over 2. And on this side I can write it as psi is equal to e to the plus c squared over 2. And therefore my general solution might look like psi is equal to a e to the minus c squared over 2 plus b e to the plus c squared over 2. And immediately I recognize that this second term will blow up. As c gets larger and larger, e to the c squared over 2 is going to blow up. Therefore, I can't allow that. I must say then that b is equal to 0. Got to get rid of it. Can't use it. So I'm going to imagine then, going back to my original expression over here, that I should be able to come up with an approximate solution if I say something to the effect that c of psi is something like some factor times e to the minus c squared over 2. I just have to determine what happens in here so that asymptotically this thing goes as e to the minus c squared over 2. Let's guess. Let's guess that this is going to look something like psi of c is equal to e to the minus c squared over 2 times some function h of c. We don't know what h is. We have to determine that. But this is what we're going to guess. Well, if that's true, let's see what happens. Let's work on it. So that tells me d psi of c dc is equal to dh dc minus ch e to the minus c squared over 2. That's really true. Of course, we need another derivative. So I'm going to have second derivative of psi with respect to c is equal to second derivative of h with respect to c minus 2c dh dc plus the quantity c squared minus 1h times, all times e to the minus c squared over 2. Okay, well, I've got my two derivatives. We can go back and plug this all into the Schrodinger equation. And the Schrodinger equation would look like this. Second derivative of h with respect to c squared minus 2c dh dc plus k minus 1h is equal to 0. Okay, this equation looks like a mess. This is going to be more of a challenge to solve. A good place to start, though, is to look for some power series. Something like maybe the solution would be something like h of c is equal to a naught plus a1 times c plus a2 times c squared plus all the way out, such that I can write it as the summation j equals 0 to infinity, a sub j, c to the j. Oh boy, let's differentiate this series term by term. So dh dc would be equal to a1 plus 2a2 times c plus 3a3 times c squared plus all the way out. And of course, that would be j equals 0 to infinity, a sub j times j, c to the j minus 1. So that's the first derivative term. My second derivative term would look something like d squared h dc. And I'm going to get 2a2 plus 3 times 2a3 c plus 3 times 4 times a4 times c squared plus on, such that I end up with a series that looks like j equals 0 to infinity, j plus 1 times j, j plus 1 times j plus 2, a sub j plus 2, c to the j. Oh boy, what a mess. Well, what we have to do then, now that I've got my first derivative, my second derivative, what I need to do is plug them back into the Schrodinger equation. That's going to make a colossal mess. But when I do, notice what happens. A lot of terms drop out. And it's going to look like this. Sum over j equals 0 to infinity, j plus 1, j plus 2, a sub j plus 2 minus 2j a sub j plus k minus 1 a sub j times c to the j is equal to 0. Boy, the Schrodinger equation's come a long way since we started, hasn't it? Because of the uniqueness of power series expansions, every single coefficient of this power series has to vanish in order for the right-hand side to be 0. They each individually have to vanish because there's no way to combine them and believe you're ever going to get this term to vanish. That being the case, since they all have to be 0, algebraically I put this together and I'll get a sub j plus 1 is equal to 2j minus k minus 1, sorry, plus 1 divided by j plus 1 times j plus 2, all times a sub j. This is what we call a recursion formula. So if you get the first term in the series, you can get the third term, the fifth term, the seventh term, and so on. A sub j, or the 0th term, you can get the second, fourth, sixth, and so on. You get it in terms of that first term. So if you happen to know a sub 1, you'll get a sub 3, a sub 5, a sub 7. If you happen to know a sub 0, you'll get a sub 2, a sub 4, a sub 6, and so on. So because we substituted our power series solution into the Schrodinger equation, the recursion formula, this formula that we obtained, is exactly equivalent to the Schrodinger equation. Got to think about that for a minute, but it's true. Let's do the following. Let's make our h of c function, that we've been trying to figure out what that is, let's make it a composite of both even and odd solutions. That way we can do A0, A2, A4, A6, and A1, A3, A5, A7, and so on. So H even of C is defined as A0 plus A2 C squared plus A4 C to the fourth plus and so on and so forth. And H odd of C is equal to A1C plus A3C cubed plus et cetera, et cetera, et cetera. First one's an even function that only involves even powers of C. Second is an odd function that's built on A1. Well, so our recursion formula determines h of C in terms of two arbitrary constants, A0 and A1. No surprise why. It started as a second order differential equation. I expect to get two arbitrary constants. Once again, though, all of these solutions are not normalizable, so we've got to find out which ones are legal. So this is what we'll do. At very large J, my recursion formula will become approximately A sub j plus 2 is approximately 2 A sub j divided by j. Thus, the approximate solution would be A sub j is approximately some constant divided by j over 2 factorial. I'm stuck, except now what I say to myself is there some other series I can think of that behaves this way asymptotically? And maybe we could make the two equivalent. And it turns out the function e to the y squared, which I can write as sum n equals 0 to infinity, y to the 2n over n factorial, looks similar. It has the same asymptotic result. In other words, we can say, write this as sum over j equals 0 to infinity, y to the j divided by n over 2 factorial. So it kind of looks like what we have over here. So in a similar way, we can look at this as A sub j is equal to some constant divided by j over 2 factorial. So at large C, where the higher powers dominate, I can write h of C as C sum 1 over j over 2 factorial C j, which I can approximate as C times 1 over k factorial C to the 2k, or approximately C e to the C squared. Now, here's the problem. If h is on the order of e to the c squared, this is a disaster because I can't normalize it. So what I'm going to do then is dictate that the power series has to terminate. It's got to terminate in order for us to obtain normalizable solution. So let's call n the highest power that we're going to allow, and we're going to truncate everything above that. In other words, let's let k equal to 2n plus 1. Generates the physically acceptable solutions. Thus, if that's the highest we can get, that generates, notice, what we set k equal to earlier. That means E sub n is equal to n plus 1/2 h bar omega for n equal 0, 1, 2, etc. So it's just like what we got in the algebraic method, but it was quite a bit more work to obtain because of the approximations that we had to make. I want to look at the recursion formula for my allowed k's. A sub j plus 2 is minus 2 n minus 1, sorry, n minus j, a sub 0 over j plus 1, j plus 2. So for n equals 0, there's only one term in the series, and we can choose a1 equal to 0, so that h odd is 0, and therefore C0, sorry, psi 0 of C is equal to a naught e to the minus c squared over 2. For n equals 1, we'll set a naught equal to 0, a3 equal to 0, and we'll get h1 of c is equal to a1c. Therefore, psi 1 of c is equal to a1c e to the minus c squared over 2. So generally, h sub n of c is a polynomial of degree n in c, and it involves only even powers if n is even, involves only odd powers if n is odd. And by the way, what are these guys called? These polynomials, these h polynomials are called generally capital H sub n of c, and they're called Hermite polynomials. And these polynomials solve the Schrodinger equation for the energy eigenfunctions, I should say, of the harmonic oscillator. The normalized stationary states for the harmonic oscillator then, we'll just put them here as sort of a way to finish it off. Psi sub n of x, going back to my original variables, would be m omega pi over h bar to the 1/4 power, 1 over the square root of 2 to the n factorial, capital H, Hermite polynomial, h sub n of c times e to the minus c squared over 2. That's my general solution for the harmonic oscillator using the differential equation method. Differences from the classical cases. First of all, you notice that the energies are quantized. There's this factor of n that enters the situation. Secondly, the probability of finding a particle outside the classically allowed range is not 0. It's small, it decreases quickly, but it's still not 0. Moreover, thirdly, for any odd state, the probability of finding the particle at the center of the well is 0. Kind of interesting compared to what we would expect for a classical oscillator. So what we have are two different solutions, they come out the same, of course, to the same simple harmonic oscillator problem by solving the Schrodinger equation either with ladder operators or with the brute force differential equation method. And of course, we'll be using those solutions as we go deeper into the course as well. That's all for today. Thank you.